Thank you very much, and thank you for inviting me to this conference. I'm happy to be here, and I'll try to entertain you as much as I can at the end of the day, so hopefully it will not be too long and too boring. Yes, you all know perhaps that Norway is a large hydropower producer, and we have the good conditions for that, of course, and we have also quite a lot of reservoir hydro providing flexibility, and we have talked a little bit about that earlier today, that we need to maintain that, but we also have of course also those hydropower plants, they actually impact our rivers and lakes. Just to mention also that hydropower has seen quite a much stronger, let's call it a little bit renaissance internationally, by the IEA, by all the climate change adaptation and needs, and the needs we have to change our energy systems. And just to remind you, worldwide hydropower is said to double by 2050. And that, of course, will not happen unless we impact even more rivers and lakes. And we have to do it the right way. So that's what I've been working on most of my career, trying to both allow for hydropower production and the flexibility in hydropower, but with as little impact as possible on the environment. And to do that, we need some tools. And of course, this talk is about how actually a tool we have developed for hydropower also could be very helpful for the Water Framework Directive implementation and seen together, what we call environmental design. But before I go into that, just remind you that what it's all about. It's about hydrology, how flow varies in time. And of course, naturally, it varies a lot, as these pictures illustrate in a way. This is also what hydropower does. It impacts the flow, right? And this is also other pressures may also impact the flow, the hydrology. It is clear. The geomorphology is the processes that are forming the rivers, or the result of that. And it depends on many, of course, different factors. And also be aware of that there are many different morphological shapes. I'll come back to that a little bit later, but this is what we are trying to find tools to help and to understand. And then we call them hydromorphology, which is actually all the things that are related to the hydrology and the morphology in rivers and lakes. Flow, riverbed, riparian zone, again, which is perhaps more detailed. You can think about the water velocity, the water depth, the turbulence, the substrate size, the substrate porosity, the physical habitat, the riverbanks, and the floodplains, not to forget. A lot of people would say that hydropower has an impact on biodiversity and fish and ecosystem. Please remember, their direct impact is on these factors, which again, of course, impacts all ecosystems. But these, all these indicators, all these processes, they are directly impacted by hydropower and, of course, also by other pressures. But this is what our starting point again. We also have to look at this, not many projects or many sectors that impact our river systems, they don't do the whole catchment, but the whole catchment is connected. We have to remember that water runs from the top to the sea and also carries sediments, nutrients, and so on, and it's all connected. And it's connected at different scales, and different scales work at different levels. So this we have to keep in mind, from the whole catchment to the water, to the reaches, to the water body, to smaller units like this little riffle, like the geomorphological unit, or even the microhabitat where a little invertebrate or a little fish lives under this rock, right? But they're all connected, so we have to remind that, which is one of the complicated things about the thinking behind the Water Framework Directive. I totally agree that we need to have units we can assess and work on, but all these units called water bodies are connected, so don't forget that. Then I'd like to stress, seen from my side at least, two dilemmas about the Water Framework Directive. The hydromorphology is called the supporting element in in the Water Framework Directive to maintain or to get a good ecology or good ecological potential. Well, I think this illustrates, I think it's a bridge and all the things under is supporting it. What if you take that away? Will there still be a bridge? No, there will be nothing. So I think we are misinterpreting the hydromorphology if we call that a supporting element, just something on the side. It's supporting, it's like it's fundamental. And it's quite clear, if you have no water, no hydrology, that's part of the hydromorphology, part of the HYMO, you will have no ecosystem, at least not an aquatic ecosystem, right? So it's actually fundamental, don't forget that. And then the thing I was just talking about, that it's quite difficult to split a catchment into units. We have to do that. We cannot work always on the whole catchment. We have to see the whole, because water is actually flowing from source to sea, and it's a continuous process going on. So these are a little bit of the dilemmas I've seen from what I've been working on with the Water Framework Directive. So I'll explain a little bit more about this method of environmental design. Of course, we have to combine ecology, hydrology, and knowledge about hydropower to make this actually fit together. And the tools we are using are designed both to take care of the environment and the hydropower production. I won't explain it a lot, but I'll just highlight a couple of things about this environmental design. It's a method to consider these things together, and it's a systematic approach. As you can see here on the side, or perhaps I cannot point, but in the middle there, it's a lot of tables. It's a lot of tables and graphs and things like that to help those who are using the system doing it systematically, putting together mostly recognized knowledge, but also new knowledge. It takes a lot of hydromorphological processes and descriptions of how that are changed and how that impacts the ecosystem, and mainly the first version of it was about salmon, Atlantic salmon. But we are developing now the same system for other species, for biodiversity, and also for other user interests like recreation or other services. Could be flood protection, it could be drought management, and so on. And funny enough, this handbook we made from this system is actually translated to English and to Chinese. And it's about salmon. Do they have salmon in China? No, they don't. But still, the same principles can be used on other species and other fish species, but also other user interests actually, or other fauna. One of the key things is to look at bottlenecks. And there is always a bottleneck. Also in natural systems, there are bottlenecks. For instance, here, as illustrated, I think for the fish population here, it's the emergent fry that is in a critical position. So this is important. We are looking for bottlenecks, and how can we improve them? How can we make the bottleneck larger so more fish comes through, or how can we help that? And doing that, we also have to remember that fish actually dies only once. So it's quite important to remember that it doesn't help if it's 1 week with no water. Well, then will there be aquatic life? At least not as before. And of course, working on this, we also have to, I think this illustrates the example when there is no water. I'm not sure if you see what's in the river now, but it's sheep. And I don't think that's quite what it's intended for. And this is not, it is very close to this drying river though, but it's dry because of hydropower has diverted water away from that. By the way, once I was showing this picture on a conference, someone came up to me and said, "These are my brother's sheep." So if someone recognized them, I think he actually used to work, no, we used to work for a hydropower company, not for anyway. Well, this river obviously lacks water, and this is another thing we of course work on in this environmental design principle. We have to find how to use water in the best way. If water is withdrawn, taken away either to the neighbor catchment, which was the case from the last picture, or if it's totally in another in another water regime than it is natural, right? So we have to look at the needs of the environment and the needs of before it was regulated. Maybe like this green line on the figure, it shows that it was, of course, high floods. So maybe we need to use this method of building block method coming from South Africa from like 20 or 30 years ago, where you look at how much water is necessary and how much is optimal for instance, a salmon here in the example, but for any ecosystem, and in different periods of the year. And then try to see if you can design it for that. Like this one shows, in wintertime, you don't need so much water, but you need to maintain a certain level. In the spring, the number 3 here, at least not necessarily every year, but once in a while, you need a large flood to regenerate the morphological processes. If you don't do that, you will not see any living river anymore, and so on. So this is an important part of it. But it's not only use of water, it's also, of course, other things that may have impacted the river, like this illustrates. It's not a natural morphological system here, at least, those pictures, showing channelized rivers and concrete instead of gravel in the bottom. So what we do there is, of course, that we have the possibility of a toolbox set of mitigation measures. We can, of course, need to have a flow release. We need also perhaps to have stable water temperature and providing an ice cover, at least in our part of the world, where it's also cold in winters. If that maintains through the climate change, I don't know. We need to have two-way migration solutions. We may also improve habitats artificially, like this picture with the gravel digger adding gravel for spawning habitat. And we can make so-called a river into the river, which is actually redesigning the upper right picture, a larger river which has less water now. We actually redesign it with some pools and riffles to maintain some kind of hydraulic diversity, as we call it. And of course, this has also to be implemented in one way or the other, either through the revision of terms of licenses or through river basin management plans. Just a small example of things we have been doing. I'm not going to show all of that, but for instance, in one river with diverted water in Norway, in the 1980s, I guess, we built weirs like this, which has quite a strong impact on connectivity, of course. Now we also use some modern methods with laser data and digital terrain models, which we use from the river. From mapping, and then we transform that into hydrodynamic models so we can simulate how can we make this better conditions, and this with the same amount of water. So you can still divert water for hydropower, but make better ecological conditions. Well, I don't have the final results here, but the principle is shown here, that you may make a more diverse ramps and channels. Instead of one big weir, you have different ramps, and you can see from the illustration how to do it. And it maintains some hydromorphological diversity, which is a word to remember. We need diversity, not only biodiversity, we need also hydromorphological diversity. In parallel to this, we have also been working, taking actually the results from this environmental design concept and working a bit further with that into categorizing and classifying hydromorphology in rivers, along the river, inside the river, across the river, and hydrology. And for that, we have made a set of indicators, about 20 of them, that we can use, and we have been selecting them, and they can be tested. We have tested them, and we still need some more testing before it will be fully implemented, I think. But I think based on this work we have done in many hydropower rivers, I think adding some of the other impacts from other sectors than hydropower, I think understanding how this hydromorphology impacts everything and how we can assess it is crucial. And as I said, I would like to call the hydromorphological elements in the Water Framework Directive rather for fundamental than for supporting. But that's my view on that. I'll soon wrap up. Just also would like to mention a nice tool which you can look at if you want to find information about mitigation measures. We recently, last year, we were one of almost 30 partners finalizing a EU project called Fit Hydro about fish-friendly innovative technologies for hydropower. So actually doing the same as these environmental design solutions are, trying to maintain hydropower production while improving conditions for fish. So there's a wiki that you can have a look at, and to see if mitigation measures there can also be used, and many tools to go along with it, and hopefully it's quite practical. This is also something we're going to maintain. The project is over. It was our responsibility as SINTEF of developing this wiki, and we will maintain it, so hopefully for the benefit of all. So that's all I wanted to say. So remember, hydromorphological elements are fundamental, and we have to maintain hydromorphological diversity. Thank you for your attention.